Hello, everyone. This is going to be the first in a series of a few videos to help prepare you for programming with C in CS260. So today we're going to talk about segmentation of memory, which is how computer memory is allocated by the operating system to programs as they're executed. We're going to talk about what a segmentation fault is. We're going to talk about the stack and the heap, which are ways we further subdivide the memory of a program. We're going to talk about malloc, which is how we request memory from the operating system. We're going to talk about static versus dynamic memory and why you would use one over the other. And let's get started with segmentation of memory. So a big part of C is memory management. So let's discuss how memory is relevant to programs. Each program in C has a section of memory allocated to it by the operating system when it's executed. So let's draw out memory to illustrate this. Memory. So we have a program, it's been executed, then it gets a section of this block of memory. We'll call this program A. And we could also have some other program B, which gets another section. Data items and structures such as arrays, variables, and pointers that are declared in your program are stored in this section of memory. So if we were to say, take a look at program A's source code, and inside here we have some declarations of, say, an integer array, also called A, of 10 integers, and maybe a character, C, that we'll set equal to maybe X. Then these are stored somewhere in program A's memory, which has been allocated by the operating system. Programs are not allowed to touch memory outside of what has been allocated to them by the operating system. When they do, this is how a segmentation fault occurs. So say, let's take a look at program B's source code. Program B code. Somehow it knows where this character C is. So the C it references is this C. And it's going to try and set C equal to A. It doesn't like X for some reason. It's trying to undo the work that program A did. So in reality, program B is trying to write into program A's memory space because that's where the character C is stored. This is not allowed. The operating system is going to hand program B a segmentation fault and it's going to terminate it. So you're going to experience a lot of segmentation faults as you're programming with C and CS260. Just remember that this is what's happening. And somehow, in some way in your program, you are writing into memory that does not belong to you. Sometimes this can be by over-indexing an array or a pointer. Now let's talk about the stack and the heap. So the memory allocated to a given C program is further divided into the stack and the heap. This is a picture of the stack and the heap. So let's expand the memory for program A. What does this really look like? Prog A mem. So we can see we have the stack that starts at the top of the memory allocated to program A, and the heap starts at the bottom of that memory. So let's go ahead and draw that out. And heap. Stock. And let's section that up a little bit. And the stack and the heap grow towards each other in memory. Okay, that's what these arrows mean. So as data is stored on the stack, it will grow down in memory towards the heap as it grows in size. As data is stored on the heap, it will grow up in memory towards the stack as it grows in size. To talk a little bit more about the stack and the heap, we need to talk about malloc. So this is just a brief overview of malloc. If you don't fully understand it here or you don't fully remember it from CS265, don't be concerned. We're going to go over this in more detail later. All you need to know right now is that malloc is used to request memory from the operating system. Specifically, it requests memory on the heap, not the stack. So if you're using malloc here, malloc 5, you're requesting 5 bytes on the heap. So looking back at program A's code, say it has an integer pointer, call it j, and it sets this equal to a call to malloc. The return value of malloc is a memory address, and it's a memory address on the heap. Let's make that 4 bytes actually. If we so wanted to assign to this memory by dereferencing j, say it's set it equal to 6, then we would set a 6 into heap memory. Okay. Malloc gives you access to memory on the heap. We can use the memory given by malloc to store data on the heap, like we just did to store this integer. So talking more generally, because we're going to get into static and dynamic memory. So all programming languages use memory to store data, obviously. There are a few maintenance tasks that come with using memory. You have to request it from the operating system, and see we do this with the function malloc. And you have to free it so it can be reused later. We do this with the function free that we'll specify later. Free is just a way to specify that this memory is no longer needed, so it can be reused by my process or another one. These are tasks that are usually handled for you in a higher level language such as Python or Java. They have what's called a garbage collector. When you're declaring a Python list or dictionary, or say a array list in Java, that is allocated for you by the runtime. And when it falls out of scope, it is no longer referenced or needed. It is garbage collected automatically. So you never deal with the allocation of that memory, and you never deal with the deallocation of that memory. It is handled for you. This, of course, is more of an overhead. The programming language itself has to do more work than the programmer. The most challenging and useful thing about C is that you have the ability to fully control memory. You also have the option of letting the compiler control it for you. This is what static memory is. But this is a bit more limited in functionality than dynamic memory, which is you controlling it yourself. So let's talk about static memory first. So static memory is also called compile time memory. It's memory that is managed for you by the compiler. It uses the stack for storing data. When you're declaring variables, arrays, and structs, these data items are stored on the stack. So going back to our code here, we said this character C and this integer A are stored somewhere in program A's memory. They are actually stored on the stack, so we can further specify their location. This character C is also stored somewhere on the stack. And this is maybe a confusing part, but the actual pointer J is also stored somewhere on the stack. It is statically declared. But what is a pointer? A pointer is a memory address. It's a number, because a memory address is a number. So the value of J is a memory address. The value of J is a memory address on the heap. So if we say this is the box for J, so this is J, and this is the value of J. The value of J is the return value of this malloc, which is again, some location on the heap. But again, the actual address that is returned by malloc is stored on the stack, because J is a statically declared variable that is stored on the stack. We're gonna describe this with more detail later in another video, but it is an important distinction to not confuse. The memory is allocated for them by the compiler when they come into scope and is deallocated when they fall out of scope. This is true of variables, arrays, and structs. So to illustrate this point, let's take a look at a really simple program here, dummy. So this program doesn't actually do anything. We're not printing anything. The dummy function does not do anything, but it illustrates static memory. So when this dummy function is called, the integer I, which is declared in the function's body, is instantiated, and it's given the value 7. that memory for it is allocated by the compiler. When we return the value of I and the function terminates, C can see that that variable has fallen out of scope and it will reclaim that memory. This is garbage collection, basically. But this is static memory managed for you. These are examples of variables that would be statically allocated on the stack, very similar to the declarations we made here. Dynamic memory is the memory you will control. You are responsible for requesting it from the operating system, and you're responsible for saying when it is no longer needed so it can be reused. Dynamic memory uses the heap. When you're instantiating pointers and using malloc to request memory for them, you're using dynamic memory. Effectively, you're using pointers to manage dynamic memory or heap memory. So this integer pointer j and mallocing space for it, this is an example of usage of dynamic memory. We grabbed memory programmatically with the function malloc. We gave it a value 6. And if we so wanted to deallocate it, we could. But we haven't discussed free yet, so I'm not going to bother doing that. Dynamic memory is powerful because it allows you to utilize memory programmatically. So this is one example, but this is really simple and not super useful. A more interesting example would be such as a dynamic array, like a list in Python. Lists in Python can hold different data types and an arbitrary number of elements. They don't start out as like a static allocation of an array that holds a million things. Like that would be really inefficient. Instead, as items are added to them, they adjust their size. They're a dynamic data structure. They're a dynamic array. This is an example of something which illustrates the point of like, oh, arrays are wasted space. Because if you know you have a program that needs to store up to 1 million bytes of data or something, or 1 million data items, you can just make an array of size 1 million. But obviously, if your program doesn't always need to hold 1 million things, then that's really, really wasteful. And this is where dynamic memory allows us to be more efficient with our program's performance. So yeah, you can create data structures that grow and shrink in response to different situations in your program. And it is one of the features that allows C to outperform other high-level languages because greater control means greater optimization. This is a pretty common dynamic. In higher-level languages, you can write programs that are more ambiguous. For instance, you don't ever have to specify types of things in Python. It just figures them out for you by the nature of the program. Things are inferred, but obviously all this inference and figuring things out takes extra work. This is one of the things that makes higher level languages slower than lower level languages that are really strict and well typed and all that. In effect, this is also one of the reasons why it's nice to do a data structures course in C, because programs in C are so much more like simple and you have to be so much more explicit. You really have to have a deep understanding of the algorithm that you're implementing in order to implement it correctly. And if you have implemented correctly, you can see every step of it. There isn't a whole lot of obfuscation in a C program. Static memory, just going over pros and cons. Static memory is simpler to use than dynamic memory. You don't have any need to worry about allocating or deallocating, so there's less programmer overhead. It's less work for you. Static memory is limited. As we already discussed, we can't adjust the amount of memory allocated for a static structure such as an array, and this potentially creates a lot of wasted space. Dynamic memory is complicated. There's a lot of opportunity to make mistakes, but dynamic memory is flexible. We can adjust the amount of memory allocated to a structure on the fly. Dynamic memory also allows us to be far more efficient than higher level languages. Hopefully you've gained a high level overview of the memory structure of a C program. Next time, we're going to go more in depth with memory and pointers. If you weren't super familiar with some of the concepts in this video, such as pointers, don't worry about it. That's what we're going to go over next in more detail. I hope to see you in the next video. Thank you for your time.